Okay, so again, in the previous lecture, we discussed sequences. We proved a few theorems about sequences. And the main definition that we had was that of convergence of a sequence. So this on the board here is the definition of what it means for a sequence to converge to a limit. Now, the notation we'll be adopting is either this, so limit of xn equals L, or xn converges to L as n goes to infinity. So in today's recording, we're just going to look at some example problems from the textbook. And I'm more or less going to be repeating these problems, but adding in all the details that you might miss when you're trying to read it yourself. So let's begin with the first, most simple example. So prove that the limit of the sequence 1 over n is equal to 0. So in order to prove this, we need to show that this sequence and that limit satisfy this definition, right? So when I was a student, I would typically have like another sheet of paper or something next to me to write on to write down what I want, right? So in order to prove that, what do you want? So we want that the absolute value of 1 over n minus 0 is less than epsilon for any choice of epsilon greater than 0. That's what we want, right? We want this to hold, the sequence and the limit and epsilon. Now, in order to do this, we need to find this integer, or this natural number k. If we can find a k, so I guess I'll underline it in yellow, we need to find a natural number such that for all n greater than or equal to that natural number, the sequence evaluated at that n is within distance epsilon to the limit. That was the whole gist of the lecture that I recorded. So what does this imply? If this is what we want, we need to find that natural number k, which is going to be dependent on epsilon. The choice of this cutoff value, this index k, depends on the epsilon that you pick. So you can think of this as like a game where you have an epsilon and you want to find an index where after that index, that's arbitrarily close to that, or within epsilon distance to that. So if we want that, we can kind of work in reverse and say that, okay, what does this distance mean? Well, that's just 0. So that's the same thing as saying that, right? Now n, since xn is a sequence, n is just some natural number, right? Sequences are functions from the natural numbers to the reals, or in this instance. So we know that this is going to be positive. So we can just drop the absolute values, right? Okay, and we want that to be less than epsilon when n is greater than or equal to k. That's what we want. So what we can say here is that, well, maybe So this is true here. This right here is true if and only if 1 over epsilon is less than n. That's an if and only if, by the way. If and only if. That, if and only if that. So notice that this is true, which implies that that's less than epsilon. That's true whenever n is greater than 1 over epsilon. So what we can do is say, I don't know, like, we can just say, take k to be greater than or equal to 1 over epsilon. So if k is greater than or equal to 1 over epsilon, and n is greater than or equal to k, then this will hold, which means that will hold, which will mean that that is less than that, which is what we want at the top. So it's kind of working backwards. We need to like mess around with it a little bit to find out what the appropriate choice of our index is. So now that we've found it, we can actually write down the formal proof. Okay, so we just say let epsilon be greater than 0 and choose k, which is some natural number, so that k is greater than or equal to 1 over epsilon. Okay. So we did the work over here to find out what that index k needs to be. So now we just need to show that under that assumption that this holds, the distance from the sequence to the limit is at most epsilon under this assumption that n is greater than or equal to k. So I'll just write it out. Then if n is greater than or equal to k, we have that the absolute value of 1 over n minus 0, which is equal to the absolute value of 1 over n, which is equal to 1 over n, right? Maybe I can do like, it doesn't matter, but the way that your textbook uses it, it's strictly greater than, so I'll do that. So if n is greater than or equal to k, right, then 1 over n is at most 1 over k. Because n is greater than or equal to k, when you divide by a bigger number, you have something smaller, right? But notice here, under this assumption, if k is greater than 1 over epsilon, then epsilon is strictly greater than 1 over k. Hence, 1 over n converges to 0 as n goes to infinity. Done. You see that, right? Like that piece right there, like this implies that epsilon is strictly greater than 1 over k. So So if n is greater than k, greater than or equal to k, then 1 over n is less than or equal to 1 over k. But that is less than epsilon under this assumption. Any questions on that? That's the formal proof, by the way, it's done.
Seems fairly straightforward.
Okay. Again, if it's not straightforward, you just have to work backwards. Like this is the proof, but there's work that goes in before you can actually write this down because you need to nail down what that index k is. And k, that index, or capital N, or whatever choice of cutoff index you have, is always going to be, I'll just say it, always going to be some function of epsilon. Like you give me an epsilon, and then once you have an epsilon, then you have to be able to choose the k that works. Then. All right, so let's do another example. Let's see. Okay, so prove that the limit of 1 over n squared plus 1 is equal to 0. Okay, so again, the game works the same. So what do we want? We want 1 over n squared plus 1 minus 0 to be less than epsilon for any choice of epsilon. So this is true whenever 1 over n squared plus 1 is less than epsilon. But again, n is just some natural number, so we can drop the absolute values. So this is what we want. But now notice in the previous example, we proved that the limit of 1 over n is equal to 0. And then notice that 1 over n squared plus 1 is strictly less than 1 over n. Now you're dividing by a bigger number, and n is some natural number, so yeah, that's true. So if we want that, we can also say, if we can get that, then we're done, right? Like, if we can make 1 over n less than epsilon, then that's less than 1 over n, which implies what we want. So what did we choose? So we choose k to be greater than 1 over epsilon. So epsilon is strictly greater than 1 over k. So that's what we did in the previous example, which will force that, which that forces that to be less than epsilon, which is the thing that we want. So it's basically the same thing though. So formal proof, say let epsilon be greater than 0, and choose k it's some natural number, which is, again, it's like a cutoff index for the sequence, such that k is strictly greater than 1 over epsilon. You know, let's write this out, which implies that epsilon is strictly greater than 1 over k. I didn't write that last time, but just to make it clear, the more clarity that you have in your proof writing, typically the better. So then, if n is greater than or equal to k, observe maybe that the absolute value of 1 over n squared plus 1 minus 0, which is equal to the absolute value of 1 over n squared plus 1, which is equal to 1 over n squared plus 1, which is strictly less than 1 over n, which is less than or equal to 1 over k, which is less than epsilon. So the sequence minus the limit is less than epsilon. In other words, the distance from the sequence to 0 is at most epsilon whenever n is greater than or equal to k. Whenever that value n gets big enough, this thing is really close to that thing, if we choose epsilon to be small. So then we just finish it off by saying, hence, 1 over n squared plus 1 converges to 0 as n goes to infinity. That's the same thing as writing that. Any questions on that? Okay. So let's do another example. Prove that the limit of 3n plus 2 over n plus 1 is equal to 3. Okay, so before moving forward on this one, I want you to maybe take time and think about what happens to this ratio when n gets really big. So for example, if n was 2 trillion, right? Does that 2 even matter, really?
No.
Does that 1 matter? No, right? So if n is big, 3n plus 2 over n plus 1, that thing basically looks like 3n over n. Basically. Or if n was 2 to the power 1,000, which is some really huge number, that is like dust. That's nothing compared to how big those terms will be. So when n is really, really big, that's basically like looking at that. You can just ignore those constants there because they mean nothing when compared to n, if n's big enough. But that ratio, if that kind of looks like this kind of looks like that. So even before writing down a formal proof, we can get some intuition as to like what's going on here. By just imagining, before we start doing anything, just imagine what that looks like if n is some unfathomably large number. And what does it look like? It looks like 3. Okay, does that make sense?
Yeah.
We have like reason to believe, right? We have reason to believe that this might be true. All right, so what do we want? In this case, we want 3n plus 2 over n plus 1. Actually, I'll do this a different way. Instead of doing it, finding the index n before, I'll do it after. It's just like a different style of writing these types of proofs. So let's go ahead and do it. Let's say let epsilon be greater than 0 and observe that the absolute value of 3n plus 2 over n plus 1 minus the limit is equal to 3n plus 2 minus 3n minus 3 over n plus 1. And now this is going to be equal to absolute value of -1 over n plus 1, which is equal to 1 over n plus 1, which is less than 1 over n. So maybe consequently, if, so we just need this to be less than epsilon whenever n is greater than equal to k. And we've been doing this game with the past 2 examples. So if k is greater than 1 over epsilon, and n is greater than or equal to k, then this distance here is less than epsilon. Because if you assume these things, and epsilon is greater than 1 over k, and 1 over k is greater than 1 over n, provided this holds, so then all of this would be less than epsilon. So hence, limit of 3n plus 2 over n plus 1 equals 3. So it's just a different style of doing it where you work out the algebra first, and then you just say, oh, if I just choose my index to be this in terms of epsilon, then that is obviously bounded above by epsilon, which means that the distance between the sequence and the limit is arbitrarily close. So we know that the limit is going to be validated and the proof is complete. Sounds good? All right. All right. All right, one last example. So prove that if 0 is less than b, which is less than 1, then the limit of b to the power n is equal to 0. So does this make sense?
Yeah, a decimal, a positive decimal multiplied by itself over and over is just going to get smaller and smaller
Right, so like for
towards
example,
0.
1/2 raised to the power n as n gets larger and larger, 1/2 is getting smaller and smaller and smaller. It's going to be arbitrarily close to 0, you're right. So what do we want? We want b to the power n minus 0 to be less than epsilon. That's what we want. But this is like saying that b to the power n is less than epsilon, right?
Yep.
B is a positive number, you're raising it to a natural number. You're right. So now we just need to find out how to like index this, how to find the index where this will be true. And I see that there's the n value is in the exponent. And typically you don't want that. You want to be able to somehow like solve for n in a way so that you can compare it to the cutoff k. So to bring that n down, I'm just going to take the, I don't know, natural log on both sides of this. Natural log is monotone increasing, so the inequality will hold. So I can just say ln of b to the power n is less than ln of epsilon. That's like one way to do it. So then using rules for exponents, it's going to be n. Well, that's just 1, right? Right? Log base e of e, which that's ln, right? That's just 1, right? So if I bring the exponent down, I have natural log of b less than 1. So then I have n is greater than 1 over natural log of b. Now the inequality flips because natural log of b is less than 0 if b is in that open interval, right? If you look at the graph of natural log, if you look below 1, between 0 and 1 on the domain, you're below the x-axis, you're negative. So when I divide both sides of this strict inequality by natural log of b, I get that. The inequality flips. So then, if I can just say, if n is greater than that, then that, then that, then that, then that, so I just have to pick k in between there and there. And if n is greater than or equal to k, then that holds, that holds, that holds, that holds. And then you prove let epsilon be greater than 0 and choose k, which is some natural number, such that k is greater than 1 over natural log of b. Then I haven't worked this out, but I'll just see if n is greater than or equal to k, b to the power n minus 0 is equal to b to the power n, right? And I'm trying to figure out the cleanest way to write it right now. That's equal to b to the power n. And actually, if n is greater than or equal to k, I know that that's at most b to the power k. Right? And then if k is greater than that, then b to the power k is strictly less than b, the natural log of b. Like dividing a fraction. And what I want, where's my f? So I want that somehow.
Sir?
Yeah.
Why does the natural log of epsilon become the natural log of e? Aren't those two different?
Oh. I'm pretty sure that COVID vaccine has a little loopy. There. Okay. I don't know what I was thinking. So let's fix this. Surprised no one else caught that. So now I can fix this. Then if n is greater than or equal to k, we have n greater than or equal to k, which is greater than natural log of e over natural log of b, which this implies that n natural log of b is less than natural log of epsilon. Which implies that e to the power n is less than natural log of epsilon, which implies that e to the power n is less than epsilon, which is the same thing as saying e to the power n minus 0 is less than epsilon. Hence, the limit of e to the power n is equal to 0. And that's it. Maybe not the cleanest looking thing, but it works. Okay, I'm gonna go ahead and stop the recording now.